Welcome back again. We're still looking on probabilities and we're focusing on tree diagram. Okay. Now, we have a problem for you and we'd like you to try with us together and let's push together and let's see what we get. So here, still a tree diagram, okay? Nothing about whether it's independent or dependent. So what do we know is a Thabo, okay? Thabo and Peter, they run a race and play a tennis match. So they run a race and play a tennis match. So the probability that Peter wins a race is 0.4. So we give it the actual probability. The probability that Peter wins a race is 0.4. 0.4 is 40%. And the probability that Thabo wins a tennis is 0.7. So that is given on our tree diagram. So we have Peter wins, Thabo wins. What are you talking about? This part, we're talking about a race. What is the chance that Peter wins a race? It's what? 0.4. If the chance that Peter will win a race is 0.4, what is the chance of Thabo winning a race? We know that the branches add up to 1 because we have 0.4. 0.4 plus what to give us 1? That will be 0.6. So we can actually calculate the probability of a known line on a tree diagram branch using the other because we know that and that add up to 1. Are you all together? Great. So the first question is complete the tree diagram given. So there's the tree diagram given to us. We need to put in something there, and there, and there. Then use the tree diagram to calculate. So we have to use it to calculate what? The probability that Peter wins both events. What do we mean events? We're talking about what? Tennis and race. Then the probability that Thabo loses the race but wins a tennis match. Okay, loses a race but wins a tennis match. Okay. So firstly, if I can complete my tree diagram, I'm able to calculate the actual probability. So let's aim by completing that first. So firstly, we knew that this was what? 0.4. That will add up to 0.6 because the sum of that and that will give us 1. And we had Thabo 0.7 there. Then this part for Peter will be 0.3 because 0.7 plus what to give us 1 is 0.3. And we get Thabo wins 0.7 there and 0.3. Then let's look at the possible outcomes because if we have a tree diagram, we can just trace the possible outcomes. So what are the possible outcomes? The possible outcome will be here. Peter wins, there is because it's Peter wins, and wins a race. Are we together? Because we're talking about a race in the first branch, and we're talking about a tennis in the second branch. So the probability that Peter wins race and tennis, it will be 0.4 times 0.3. 0.4 times 0.3, which will give us 0.12. Now, the probability that Thabo loses a race, are we together? Loses a race and wins a tennis will give us what? 0.4, because he loses a race, which is what? 0.4, where's 0.4? 0.4 multiplied by 0.7. There's Thabo. Okay? Then the probability that Thabo wins race and loses tennis, okay? Thabo wins a race, 0.6. We're looking at that branch, 0.6 multiplied by 0.3. Okay? So we just multiply your branches. Then Thabo wins a race and tennis. Race and tennis is 0.6 times 0.7, which is that branch multiplied by that branch. Okay. So this is what we get. Okay, our probability. So the probability that Peter wins both events. So Peter wins both events. We can see what we're getting here. Okay. Peter wins a race and tennis. We get 0.12. 0.12, which is 12%. That's the chance that Peter will win both events. But what about the probability that Tabo loses a race but wins tennis? Okay, Tabo, that would be what? Tabo loses a race and wins tennis. It would be 0.4 times 0.7, which is 28% or 0.8. We all together. So if I have my tree diagram, I'm able to calculate whatever question that comes out in terms of the probability by just using my branches. Okay. Now, let's look at what is dependent event. Okay. So two successive events are said to be dependent if the outcome of the first have an influence on the outcome of the second event. Very important. Are we together? The outcome of the first have an influence on the other outcome. Those are dependent event. Okay. Let's look at what that looks like. So Jabulo has 10 colored cubes in a bag. 3 of the cubes are red. So what we know is that 3 of the cubes are red and 7 are blue. So 3 red, 7 blue. We all together? He removes a cube at random from the bag and note the color, but does not replace it. Very, very important. Put his hands in the bag, note the color, does not replace it. If I don't replace, I have 10 cubes in my bag. I get one color. I don't replace it, what changes? What happens? Now I have 9 balls. If I have 9 balls now because 1 ball gone, what does that affect? My total sample space is no longer 10, it's 9. And I can do the same thing again, remove another one. If I remove another one now, how many balls left in the bag? 8. So it affects the sample space. It will affect the probability of the next event occurring. How will this tree diagram look like? Okay, let's see. So let's record the information in a tree diagram. So first choice, we have red and blue. So the probability of red occurring is 3 out of 10. Why? We have 3 red. So it'll be 3 out of 10. And what about the probability of what? Of blue? It'll be, are we together? 7 out of 10. Because initially, we still have 10 balls, nothing. We have 3 red, 7 blue. What is the probability of getting red? 3 out of 10. What is the probability of getting blue? 7 out of 10. Then you draw our tree diagram. This is what we get. You draw your line. This is red. But now, we don't replace it back. What will change now? Will the probability still stay 3 out of 10? No. Because we don't have 10 balls anymore. Now, if we took red, we take red outside. We don't replace it. We have 9 balls, but how many red? Initially, we had how many red? 3 red. Now we'll be left with 2 red. Are we all together? Now, for blue, we had 7 blue balls. What if I take blue? I put it aside. What changes? I don't have 10 balls anymore. I have 9. But how many blues? 6 blues now. Because I've not replaced it back. Are we together? So it affects the branches of the probabilities and the actual probability. So let's see now. The chance of getting red will be, so we can get red, blue, and blue, red. Of getting red now will be 2 out of 9 because there's 2 blues now because red is out and the size now is 9. Probability of getting blue. Blue will still be what? We'll still have 7 blues inside because we have not touched any blue. But how many totals? 9. We'll have 7 out of 9. This is what we'll get there. And if we had blue for the first time, let's say we get blue, and then we get red. What changes? We'll get 3 out of 9 because there'll still be 3 reds. But blue out, now we don't have a total of 10. Agreed? We have a total of 9. And what about blue? What does this mean? Blue is out. 1 blue out. We have initially 7 blues. Now we have 6 blues. And the total in that bag is no longer 10. It's what? 9. Then we'll have what? 6 out of 9. This is what we get. The probability of getting red, you just multiply that branch and multiply that branch, which is what? 3 out of 10 times 2 out of 9. Similarly, blue, red, multiply together. And what about blue, red again, or still blue, red, which is 7 out of 10 times 3 out of 9. You multiply, you get 21 over 90. The probability of getting blue, blue, that is the line, and this is what you get all together. So this is what it means. These are all your possible outcomes. A replacement and no replacement. Remember, when you don't replace it back, it changes the sample space and it reduces the other colors. Are we all together? So the probability is really affected. The probability of one event occurring affects the other. Okay, guys, fantastic. We'll take a short break, and when we come back after the short break, we'll look at more problems. And we encourage you to keep working hard and to push hard. We will definitely see you shortly.